Hello and welcome to a talk on the Libre-SOC project for EuroPython 2021. So we use Python for pretty much everything in here, and I just want to take the opportunity to go over that. Now there's quite a lot to cover, so I just apologize in advance. That is going to be very much of an overview, but I just want to give you a glimpse into the different aspects of where we use Python in this project. So the first thing is that it's a Python simulator of the power instruction set, which we use for experimentation. It's only about 2,000 instructions per second, but we don't care. It's written in Python, and that's more important for code clarity than anything else. We use Namitan for the HDL. HDL is a hardware definition language. Now this includes a simulator, its own simulator, so it will do gate level simulation similar to Verilog and other simulation tools for HDL. And excuse me, we then compile that to using a program called Yosis, which outputs Verilog, which is a more standard language, but we treat it in this case as a machine code target. That Verilog is then handed over to Coriolis 2. Coriolis 2 is written in a mixed Python and mixed C++ and Python. It's a VLSI tool, so it's a complete tool chain. So you specify the program and the layout in a Python program, and it will then action that and create right down to the GDS2 files for you. And you can then send those to Foundry and get a chip back. So the other thing is chipsfilmmakers have created a cell library, which is needed here. We'll go over this a bit later on. Chipsfilmmakers have created a cell library, specifying it in Python, where you run the Python program to generate the cell libraries given what is called the PDK, the Physical Design Kit, for the Foundry. Now, in most cases that's under NDA. However, fortunately, there's a couple out there. One of them is Free PDK 45, which is an academic PDK for training students. And there is recently Skywater have released their 130 nanometer PDK. Normally, you would do this under NDA because I think so. Staff himself has to run. He has specified, for example, the TSMC 180 nanometer PDK. He's got access to that. So under that NDA, he generates the cell library. He runs the program, which generates the cell library, which is suitable for TSMC 180 nanometer. He can't tell us what that is, but at the high level, we can run a parallel path along the way using the free PDK 45, so we can track what we're doing. That's what we did for the 180 nanometer ASIC with when working with Sorbonne Lib6. Now, so I'd like to explore Namitan. It's quite an absolutely fantastic HDL, very well documented. There's tutorials online, things where you can see. I think now just briefly here. Here's your module. It has two signals. It has here, there's a count, so on each clock sync is a synchronous clock, so on the next clock cycle count will be equal to count plus 1, and if there's an overflow detection, so if it hits a limit, it will set, that's combinatorial, so there's no time limit on that. It's always enabled, always generating a signal. And if that overflow is detected, then on the next clock cycle, the count is set to 0. Else it's count plus equals 1. So here you can see it's just a counter. Now what's really nice is that we have standard Python classes and modules with the expected behavior of documentation, which of course Sphinx understands and creates what you need. So it's absolutely fantastic. As far as readability is concerned and expectations, Verilog, Verilog hardware engineers are not software engineering trained, and it really shows. So here's the repositories that we've got. I think it is a proper Libre project. So we have this. We have mailing lists and mailing us archives, and we also have an IRC channel, etc., etc. So development is done in real time. It's not done according to the I'll do it when I'll release it when it's ready thing. We are a Libre project. So just to say, if you'd ever like to help us or have a set of procedure we can go through, it's documented on the website. Here's how to get started, and this is much easier just by using what we call the dev-env setup scripts. So you can just run those in an automated fashion. For example, here there's that cloning of those repositories. Then running the Python setup with PyDevelop. That's to make sure it's in place so you can actually edit the code. We don't do Python setup and install because you need to be able to edit the code in place. Things, and off you go. And likewise, install the dependencies. I think another script there. So it's all documented and easy to get set up. One for CocoaDB, one for Icarus Verilog, etc., etc. So we picked OpenPower because it's a supercomputing instruction set with a 25 years history. So the end user license agreement was okay, absolutely fine. I had a very nice chat with Mendy from the OpenPower Foundation about it, and it's very, very reassuring. The OpenPower Foundation, most things have been absolutely fantastic about this project. It's really quite exciting. So what we did is, as software engineers, you don't do stuff by hand if it can be done automatically. So what we decided to do was to extract information from the OpenPower specification and to put it into a machine-readable format, and then first write a decoder and a parser, and including a simulator. All right. So the first thing we had to do was to decode the major opcodes and the minor opcodes into tables, and these are like microcode ops. All right. Now these originally, so you can see that major opcode 34 is a load store operation, and it's the instruction LBZ, OpenPower. Right, now, interesting, all of these actually came from Microwatt, the Microwatt source code, which has been a fantastic reference implementation that we used. It's in VHDL, but both Anton Blanchard and the rest of the team are software engineer trained, so they put code comments in and did continuous integration unit tests, and etc., etc. So we extracted these tables and put them into machine-readable CSV files. Okay, and then put them behind a wiki. Connecting. Give it a moment. Whilst that's loading, I'll do this one as well. So what we also did was we extracted the pseudocode from the specification now, and split it down into separate pages. So, for example, oh, I know what's going on. My internet connection's gone. That's annoying, but I have to wait for that to come back. Let's go and have a look at the source code here instead. So %2. So here is the markdown files which this is for the store B instruction, for example. Now that D form there indicates that it is to be indicates the layout of the fields. So here's your specification. Store word D form. All right. So there's your pseudocode, which is in the specification. Now the specification actually says we're not supposed to make this. This is not supposed to be executable. We went, nah, forget that. Saying we're making it executable. So because it's correct. We know it's going to be correct. So that's store B. STW. There's STW for us. There's deform. Now the deform says that the layout is as follows. Okay. In bits 0 to 5, there will be the number 36, which is the store W, and then RS is in bits in field bits 6 to 10, RA is in 11 to 15, etc. Now that table, the one I was saying, %1, find D form. D form, capital letters. There we go. Right, here's one of the deforms. So, which one was it? D there. D. Yes, this one. Okay, all right. And this is an machine. We deliberately made it machine readable. The rest of the specification has. Let's see the failed. Find RT. Field RT. Here. So again, this is in the specification, and this is machine readable. All right. In a Python program to thing, and you can see that was the D format there. All right. So the next go. So the next bit in the puzzle was to actually convert this pseudocode into executable Python, right? And for that, I decided I absolutely love PythonPly, all right? So I recovered the garden snake example, which is a subset of Python, and I fixed several of its errors. Ply is an LALR parser based on Yak and Flex. Yak, Flex, Bison. But Python, the actual language itself, Python, doesn't lex properly in a single pass. It turns out that you actually have to do some fixing of some of the indentation. So I did in the lexer, I look for the tokens and add an extra indent token when the opportunity is detected, and de-indent and track it, and that way are able to turn it into something that can be properly parsed by an LR parser. Now, there was also a few other things that needed dealing with. Silent keyword fall through in things. It also skips some blank. It takes blank lines, and also the syntax here. It turns out to be this syntax turns out to be Python-like. It's not exactly Python, but it's close enough that I was able to adapt the garden snake thing. So I changed the tokens. Rather than colon if test colon, I used if test then, and inserted the token. So that's what this program does. Is oh, there we go. If token type equals then replace it with a colon, and if it's an else, then we want to yield the else keyword and also add in a colon, because that makes it a Python syntax. So same with do, etc. Right. Then so the next thing was we actually have to have a page reader which reads the syntax of the things and extracts that pseudocode and these forms. This is actually a very important part of what we're doing. Followed by finally an actual parser, which if you're familiar with Python-ply, you have the BNF back as now format syntax in the comment field. It's a fantastic idea. The latest version of Ply actually has it as a decorator, which is kind of nicer because then you can then use the comment field for actual comments. And in this way we end up with some code. VID coder ISA fixed store.py and it and what was stw, and ta-da, we end up with an operation. This is what the compiler outputs. All right, so memory sign there, assigns to memory at that address, and there's all the that's get register or 0. Lots of little hacks like this, but it calculates the effective address plus sign extends on the immediate. Notice here that the immediate is not actually in here. What we've done is we've done a decorator which injects local variables into the context by actually altering the globals and the locals of the function. Yeah, I know. And then on exit, it will extract anything that's been modified. So in this case, that same function will extract RA from the namespace or any other variables that have been modified. So that's how that operates, and so we can write our own simulator. Now let's have a look at one of the better. Yes. Okay. So let's have a look at this one now. So here we're actually running the simulator. Python simulator. So those instructions got decoded in Python by machine reading those formats. So where we have this fields format here. Sorry, a second. So where we have this format here, we match that against the relevant instructions format here. Excuse me. So then we can pass in some initial memory values that we want to do, and then run that simulated instruction, and assert and compare it against the expected value afterwards. And we do thousands of these tests. Now, to double check this, we weren't confident that we got it right. So what we did was went, well, there's an implementation of power instruction set simulator. It's called QEMU. Why don't we use the machine GDBMI GDB machine interface to actually connect to QEMU? And here's your arguments for the one running little endian or big endian, no graphics thing, and start it up, and then upload the program, the exact same compiled program, to QEMU, and then upload memory. All right, so do the exact same thing and upload some initial memory values, and run the program, and then check the registers afterwards. And in that way, what we can do is we can do co-simulation side by side of QEMU with our simulator, all from Python. Right? And then we do the exact same thing with the HDL. So we're doing this bootstrap process, which develop a very slow simulator in Python because it's easier to read and read and understand. Then cross-reference and check it against QEMU by co-simulating the R simulator versus QEMU. Once we find that that's correct and it can run, we have confidence in our simulator, we go back and run the HDL, the Namitan simulations, against the Namitan simulations against the Python-based simulator. All right. And run, thousands. I mean, it's literally thousands of unit tests just to make absolutely sure that we're confident in what it's doing. Now, let's have a look at the add instruction here. Fixed point load and store, fixed point move and assist, fixed point arithmetic instructions. Okay, add, right, brilliant. Okay, so here's the add instruction here, which add immediate. All right, let's do the, no, not that one. Brilliant, add RT equal RA plus RB. All right, brilliant, okay. So we divide it down into separate pipelines. So let me show you those. Push T -1 function units. So there's an ALU pipeline branch condition register div unit, and these are divided down by the profile registers. So anything that needed a similar number of read and write registers, we put it in the same pipeline. So this is Namitan elaborate. Bear in mind, here's that operation comp. Let's have a look. Here's your switch statement. Now it's switching on the instruction type. That instruction type comes from the. Let's actually search for op add. Oh look, there we go. Op add. There we go. There's all the add operations here. All right. So it says you want to read RA and RB operations. Notice, you remember from the specification, it said it needs RA and RB. All right. So this. Oh, it's back. Brilliant. So op underscore add. Here's our version. That's op immediate. So this is the CSV files which are read by Python. So that's add IC, add integer with carry instruction is that one. Dump. Minor code 31. That's the equivalent of the thing. So here's the code comment, add instruction. All right. So adds RA to RB, and the destination is RT. And oh look, it can do condition registers as output. So switch statement, it's written in Python. It's got comments. Duh. So here's your add. So what we're doing here is we're actually doing a 65-bit add, which allows us to do the carry, and then the carry overflow is a 32-bit, the 64-bit carry. So that :-1, that takes the 65th bit. And here's a calculation for the 32-bit carry overflow, which came from Microcode. So sign extend just calls a function, and again the switch statement is if the data length is one thing. So this is for extb, ext half, and extw, the different instructions available. And then we end up joining all those together, those pipelines, etc., I think I'm going to have to move on quite quickly because we're starting to. There's quite a lot else to cover. So now, once that's all done, we can then output it as Verilog. Jobs-fly, simple. Issuer Verilog. So again, we can generate a core here with different options, because those options are passed in to the program, which in a config file, it will in a configuration object, it will Python. The whole reason why we're using Python is because we can enable at compile time, this is compiling into Verilog, we can, oh, there we go, there's your options, the specification. We can pass this in and then do if reg width equals this, or if we want the Zix controller, interrupt controller to be generated, then output certain stuff into the Verilog thing. So for the Libre-SOC 180 core, which went to ASIC, we needed a way to add 4 SRAMs, 4K SRAMs, but running the simulations, we didn't want that, so we made it an option here. Right. So there's the Namitan Verilog convert. Now, once that's converted, we can then run a simulation. Okay, and this is compiling that up, and off it goes. And now, one of the other things that you need when developing an ASIC is you need a JTAG interface. So you don't think, when you just take it for granted. If you've ever done embedded computing development, you just take it for granted that there's going to be a JTAG interface. Well, somebody has to implement that. All right. And very kindly, Staff Verhagen from chipsfilmmakers made some Namitan HDL, which implements a fully functioning JTAG tap interface. And we've been able to think, so we can set the manufacturer ID, and then when you put that either into FPGA or ASIC, or in this case in a simulation, which I'll show you in a minute, you can get that manufacturer ID back. But one of the other things, Wishbone, one of the things we needed was the ability to upload programs over JTAG. So because we're using a Wishbone interface as the bus, Staff added the ability to connect to the Wishbone interface over JTAG. And through this, we're able to actually upload programs even to the simulator. Now, I don't know if you're familiar with OpenOCD. It's basically a way to manage hardware. But in this case, what we're doing is we're managing the simulation. So we've got a JTAG interface operating here, and a remote bit banging interface is connected up. So whilst that is running the BIOS, we've connected over OpenOCD and sent some commands to it. TDI transmitted the data and TDO. It has connected and found, oh look, there's a manufacturing ID. Well, hey, there's that ID 018FF, which was a set part number 0001. So that's from here. Where is it? Dun, 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 dun. Part number 001, and if you convert that, you'll find that that was 0x18FFF. So from here, we can write some scripts, and let me see if I can find them. ls debug. Yeah, vi debug SAS firmware upload. This is the this is a command which, if I run this, it will actually upload a program using the same test stuff that we did earlier. So a very simple loop program using the same compiler, etc., to generate instructions. We can pass those compiled programs into over the JTAG interface to the system that we're connecting to, uploading it in over Wishbone, and remotely controlling it. Now, what's really nice about this is that the exact same program, the JTAG command system, can be used on the simulator and the FPGA and the emulator once we extract from the simulator from the VLSI tools and resimulate the HDL after it's been laid out. And when we come to it, we'll have a series of programs that when we get the chip back, we can actually test the things. And it's exactly the same code each and every time. Right? We're checking again and again and again and again at every single level that that what we're doing actually works. Now, let me leave that one. Now, so here was the simulator, which was the Verilog code, which was after it was let's Libre-SOC Libre-SOC.v. So here was the machine code looking Verilog after that's been on Namitan outputs this from its HDL. It will create this very grungy looking Verilog for you. We don't actually want to be reading that code. But what we do want to do is we want to hand it over to Coriolis 2. Now Coriolis 2 is the HDL automatic layout tool, and let's have a quick look here at an example program. Now this is a very simple ALU, which is very useful for what we're doing, so let me just quickly explain it. The top layer module has an op, which is a signal field. It has two input signals, A and B, and it has an output of bit width. So these are HDL signals of width, and when we declare the class, we want to go, we're declaring it as width 16. Fantastic. All right. So now there's an adder module and a subtractor module here. Let's have a quick look at those. So the adder module has an A and a B as input, and it has O as an output. And oh look, in combinatorial logic form, it adds A to B, and that's your output. Go figure. All right. And the subtract one, oh look, that does a subtract of A from B. Wow. All right. So what we then do is, depending on whether op is true or false, on the next clock cycle, the output will be set either to the results of the subtract or to the results of the add. Now, I want to just think this. What I've found is that it is incredibly important to view these things graphically. As I didn't do gate level design or hardware things. I learned this on the fly. All right, so here's your input A and B, which is A and B are passed to the adder and subtractor modules. The outputs come from here, and then there's depending on the op here, it will do produce that output. Now, if we do ProcOptSynth. Now, I don't normally do this, but I did want to show it to you because it's it shows you right down to the gate level. Now, what this has done is it has taken that the cell library and gone down to individual cells. So it's split out the bits of A and B, received the output, and where is op? Yes, op goes into each individual mux here and selects one in each of the bits of A and B. And you don't normally see this kind of thing when you're dealing with high-level stuff. And then it goes into a flip-flop to capture that output from the mux so that it's stable so it will be available for the next clock cycle. And then each output, bit 0 of each one, gets put together and it goes into O, the output here. Okay. All right. Now, here's one I prepared earlier. All right. This is what the actual chip looks like when it's done the layout. Okay. Whoops, I always get that wrong. And here's your individual transistors within the cells. Okay. Now, in this particular program, what I did was and this is a beautiful thing about Coriolis 2. I did a manual place of the adder on the left side and had a manual place of the subtractor on the right. And then I did a manual place on the individual components of the cells in the muxes, and then and from there I asked it to do the routing. ask Coriolis to handle the routing. But all of this layout here was done. I specified these locations of where I wanted this stuff to be in Python, and I specified in a Python program where I wanted the add block to be, and the subtract block to be. Now, you can't do this kind of thing without having some kind of verification. So what we did was a part of Coriolis to what it does is it extracts, once it's done this layout here, it re-extracts the net list for you into a subset of VHDL. So what we then did was passed that VHDL over to a CocoTB simulation. Which I've just got to find. Right, CocoTB. CocoTB is again similar to what we're doing inside the testing, except what it does is it takes where Namitan has its own simulator, and you can run a side-by-side simulation of HDL versus some Python code. CocoTB does the same thing, the exact same thing for Verilog and VHDL. And so consequently, when we have this VHDL here, we can put it back into CocoTB and simulate it. And oh, look, we can run the exact same JTAG tests that we did earlier, including uploading over Wishbone, sending Wishbone commands. This is, I apologize, it's quite hard to understand, but here's the command for read and write, because that saves things. So we're writing the Wishbone address here. We want to write to data address 00001, and then we want to write to memory and then read back again. So we write the binary data here, and then read back, and then do an assert to make sure that the result, standard Python assert, to make sure that the result comes back is what we expected. So that's basically what we've been doing. I'm terribly sorry, I'm running out of time for in the talk length, so I just have to go briefly over these other things. One of the things that we're also doing is implementing instructions. So we're doing our own advanced instructions, adding those to draft to the Power instruction set, because that's the funding that we got from NLnet to do this. And so the one I'm currently doing is a discrete cosine transform, which start off from the original code. The best implementation I'll be able to find is of a recursive one of Project Naoki. I then turned that into an iterative variant, and then used Python iterators to express the triple loop that this is in. DCT is usually expressed recursively. I had to create an iterative version that has 3 triple loops, and then I created some Python generators which generate those so that we can use them in the simulator and in the HDL and check that things are going on. Anyway, very, very briefly, if you'd like to help, we do actually have funding available in several different areas. This is one serious computer science project, mostly written in Python. That NLnet have very kindly been supporting us in this thing, in this endeavour. So that's Coriolis 2. We have a script for an automated install of it, so you don't have to go do the mess about trying to work out how to get it up and done. It will create a Debian S-root in Debian 10 for you. And again, that's the chipsfilmmakers website. If you want to do your own ASIC, he will help you, and he's also a Python programmer. All right, so. Yeah, if you would like to help, here's the procedure. So yeah, well, thank you very much for your time.